Welcome, Dr. Shahbandeh. Hope I said that right.
Hi, thank you. Yes.
Excellent. We're going to do a little bit of club news first here and a quick election, and then we'll get right to you in about 15 minutes, if that sounds good.
Yeah, sounds good. Thank you.
Awesome. Thank you. All right, folks, it's 7 o'clock. Let's get this party started. Where is John Pinto? Well, I just might have to run this election myself. Nothing wrong with that. All right, well, let's dive right into club news, shall we? So welcome to our October general meeting, folks. It's definitely not a good night for observing tonight, so thank you for joining me here online. I think we're under every weather advisory that exists tonight, so if I get sucked into the land of Oz and meet some munchkins later on, well, it'll be an interesting show. Some quick club news. So remember, if you are interested in purchasing an Alcor calendar or handbook, be sure to respond to the thread on Groups.io by the end of the month, and John Pinto will gather those up and make sure those orders get placed. Also, maybe this weekend we'll have a dark sky viewing event at Geneva. The weather forecast is a little bit dicey, so we're kind of waiting to see what the forecast does tomorrow. Friday definitely looks like a washout, but Saturday night there's a glimmer of hope for Saturday night. So watch for news on that tomorrow. And also on Saturday is the partial annular eclipse here in Central Florida. Derek is out in Utah, and he's setting up, hopefully, with a Starlink dish to actually live stream from the path of maximum annularity, if that's a word. And I'll also be live streaming from my front yard here to show the view from Central Florida. Again, weather permitting. The max coverage here in Orlando will be around 1:30 p.m. So if you can't watch with us, at least get your eclipse glasses or your solar filters out and try to catch a peek of it. Also, in other news, on December 16th, our holiday party is coming up. That's going to be held at the Geneva campus inside the classrooms there. So stay tuned for more details on that. We're still putting together all the details on the amenities and the program and whatnot, but we're definitely going to do it a little bit different this year. So stay tuned. It should be good. Upcoming outreach events, a bunch of them coming up. So the planetarium's grand reopening is coming up on November 3rd, which is going to be a big deal. We'll be soliciting some CFAS support for that to help get some scopes out there for the public and make that the big deal it should be. Also on the 14th, we have also at the Orlando Science Center an eclipse viewing event as well. And I know some of you have signed up to support that event as well. So thank you for everyone volunteering and doing outreach. And there's also another Orlando Science Center event, Science Night Live, coming up on the 21st that you can also sign up for. And at Winter Springs Elementary, I used to live down the street from there. There's an Observe the Moon event going on at 5 o'clock there. So if you're able to support that, you can sign up for that as well. Also coming up in November 13th, Bridgewater Middle School is doing an astronomy event. So waiting for more details on that. If you're interested in participating in any of these activities, please contact outreach@cfas.org or just respond to the threads about this on cfas.groups.io. And thanks to Douglas Woods for being our outreach coordinator, by the way, and making all this happen. Quick note. So I want to give a real big thank you to Kent Allingham. I don't know if he's online right now, but Kent was our treasurer for the past countless years, since as long as I've been involved in the club. He was unfortunately taken away from us by a health condition, so he's off battling some issues there, and we've had to kind of learn the hard way everything that he has been doing all these years that we've been taking for granted. So thank you, Kent. Managing a 501c3 is a lot of hard work, and you don't know what you got till it's gone, you know? So thank you, Kent, for all your hard work and all your years of dedicated service to CFAS. As a thank you, we voted to give you a honorary membership for the rest of your lifetime. So ignore any renewal messages you might get, Kent. It's all on the house from now on. Thanks so much. Also, I want to welcome some new committee members on the board of directors real quick. Isabel Chaufeton has joined us as the social media and events chair. Rob Fleming, thank you, has stepped up to help out on the webmaster stuff. So we're working together on designing a whole new cfas.org website. Franz von Steen has also stepped up for the science committee, and we hope to make that official with the next board meeting. You may have noticed he's been posting some science news in Groups.io lately. That's why. So thank you, Franz, for getting involved. And if you want to get involved in the board, contact president@cfas.org, and I'm sure we can find a place for you. Today's agenda, we're going to start with board elections. It is something we have to do every October, so I'll be handing over the mic to John Pinto shortly to manage that. I got a little poll queued up here ready to go for that. Also, our main speaker tonight is Melissa Shahbandeh. sorry, Unraveling Cosmic Dust Origins. She's from the Space Telescope Science Institute. How cool is that? So she gets to play with the James Webb Space Telescope all day and share what she's learned about cosmic dust. So looking forward to that. We've decided to bump Luke Corwin, or well, Luke's decided to bump himself really in the interest of time. So stay tuned next month for his talk on ghost particles from the sky and introduction to neutrino astronomy. That should be a good one as well. Thank you, Luke, for putting that together. Looking forward to that next month. And John Pinto will be back using astrology. Yes, I said it in the Old Farmer's Almanac for Astronomy. Don't freak out. There's actually some legitimate astronomical tables in that portion of the Old Farmer's Almanac. So maybe we can use that as sort of a bridge between those two worlds with people. And we'll close off with the Astrophotography Showcase as always. And with that, let me hand it over to John Pinto real quick for the election slate for 2024.
Thank you, Frank. So this is hopefully going to be very quick. Looks like we do have a forum. We've got 27 participants. So we have a very clean slate of officers who will be joining our board, assuming that you all agree. As you can see in the screen here, Frank Kane is running for president. Derek Demeter is running for vice president. Denise Woody is running for secretary. John Frank will be running for treasurer, and I am running as a board member at large, number one, redoing my stint on the board. So,
thank you, John.
Frank, you're going to throw a poll up there so people can vote.
Off it goes.
And please vote yes. That's all I can tell you. Okay.
Looks like we have a complete response, and 100% have voted yes. So thank you, everyone. Yay, we have
all our new board members.
Yep. Yes.
Thanks for stepping up.
All right, cool. Let's end the poll. And thank you to everyone serving on the board of directors. It is a volunteer job, so you know, there's no glory, but we're all doing it to try to spread the word of astronomy and bring people together with a common shared love of the night sky. And thank you to the outgoing president, Tricia Smedley, as well, and for her year of service. Running a registered nonprofit is a lot of work, it turns out. So thank you for everything you've done, Tricia. Looking forward to what we can do in the coming year. Tricia will be serving as the education chair, I believe, going forward. So she'll remain active in the board and in the club. And with that,
we very much value Tricia's participation on the board. She's always been a valuable member, and we look forward to working with her in the coming years. Thanks, Tricia.
Absolutely. She's a fountain of energy and ideas. So thank you again. All right. And with that, I will introduce our main speaker. Let me stop sharing so I can let somebody else share. All right. Dr. Shahbandeh, welcome, welcome, welcome. We have this whole huge bio from you, but the short story is you spent a lot of time in Florida State University up in Tallahassee, not too far from here. And looks like these days you're up at, are you basically at John Hopkins now, right?
Space Telescope.
Cool. All right. So yeah, welcome. And we're very honored to have someone from the Space Science Telescope Science Institute. Got that right. Yep. Talking about cosmic dust and playing with the James Webb Space Telescope. A little bit of housekeeping before we kick it over. If you do have questions for Dr. Shahbandeh, use the Q&A button down at the bottom of the screen there. And if you have any questions about cosmic dust or what it's like to play with a space telescope, I know I do, submit your questions there and we'll get to as many as we can once we're done. So let me hand it over to you and let me make sure you can share your screen. Make you a co-host just to be safe. You should be good now. Yes, we're good. Thank you.
Hi, everyone. My name is Melissa Shahbandeh. I'm currently a postdoc at the Space Telescope Institute. So I got my PhD last year at Florida State University, and I love Florida, and I'm happy to be here. Thank you for inviting me. Feel free to ask me any questions and interrupt me. I'm happy to answer your questions. So today I'm gonna talk to you a little bit about what I've been doing in the past year at the Space Telescope Institute, mostly about supernovae and cosmic dust. So what I'm gonna talk about today is not just my work, it's a collaborative work. A lot of people have helped me to get the results that I'm gonna show you, and I wanted to acknowledge their work. So I work at the Space Telescope Institute. This is an institute in Baltimore City, in Maryland. Most of, actually all the space telescopes that have ever been built or gonna be built, the center for space telescopes are Space Telescope Institute. Currently, JWST and Hubble Space Telescope are being controlled from Space Telescope Institute, and we have future projects coming up, such as the Roman. And if you have any questions about these, let me know. And I have my email on my slides. I'm happy to answer your questions even after today. So we have a transient science group at the Space Telescope Institute. So transient science, I'm not sure how much people here are familiar with transient, so I'm going to give you a little bit of an intro. When I talk about transient science, I mean the astronomical phenomena that are transient. They don't last as long, such as supernovae. They explode. We can see them from the ground or from the space for a couple of months, and then they get too faint for us to be able to observe them. So I'm part of this transient science group. You can see some of the people that are in our group in this picture. We have 4 PIs, several postdocs, grad students, and we work on several JWST, HST programs that focus on supernovae, GRBs, gamma ray bursts, tidal disruption events, and other transient events. So most of my talk is going to be focused on cosmic dust. And you may ask, so why do we care about cosmic dust? So cosmic dust is the building block of the universe. Cosmic dust is behind star formation, planetary science, interstellar reddening. And if we can understand cosmic dust and the origin of the early cosmic dust in the universe, then we can understand how objects absorb and scatter light better. We can also get information about the temperature, density, the heating, cooling rate of where dust is forming. We can also get more information about the late stages of a massive star evolution. So why supernovae? So first, I wanted to tell you a little bit about supernovae. So supernovae are either a thermonuclear explosion of a white dwarf, or they are core collapse of a massive star. The way we classify supernovae, you may have heard supernovae type 1, type 2, 1b, c, 1a. So the way we classify them is using their optical spectra. We take a spectrum with an optical telescope on the ground around where the supernova is at maximum light. And then we use the features that we see in the spectra to classify them. So if they have hydrogen, then we classify them as type 2. If they don't have hydrogen, they're type 1. And if we can find silicon in their spectra, then they're going to be type 1a. If they are type 2, if they have hydrogen, there are several other subclasses. I'm not going to get into the details of those, but today I'm going to focus on type 2p supernovae. These supernovae are the ones that before explosion, they were a massive star that they had all their outer layers intact, meaning they still had their hydrogen and their helium intact and not lost yet. And then I'm going to talk to you about type 1bc or stripped envelope supernovae. These are the ones that have lost their outer layers, such as hydrogen and helium. So why do we care about cosmic dust and supernovae? The reason is that thanks to JWST and some infrared telescopes in the past 2 decades, we've observed a lot of dust in the early universe in a lot of high redshift galaxies. which tells us that there is a significant amount of dust in the early universe. So initially, in 1960s, 70s, 80s, scientists believed that AGB stars are behind this dust formation in the early universe. But AGB stars are stars that are much younger. And at the time that we observed this significant amount of dust in the early universe, they weren't old enough to have shed their outer layers and produce a significant amount of dust. So the alternative scenario to what could be producing the significant amount of dust in the early universe is supernovae, because specifically Korkov supernovae, they are massive stars that they can shed their outer layers and they explode, and they can spread a lot of material in a very short amount of time and efficiently in the environment. And therefore, they can be the main producer of dust in the early universe. I just want to reiterate that the reason we care about cosmic dust is because we really don't know much about it. We can see dust in the infrared light, and we haven't had that opportunity before. And understanding dust can help us understand all the other objects in the astronomy better and how they scatter light. So now, why do we use JWST, and why I'm gonna talk to you about JWST results. So the reason we use this telescope to study dust and supernovae is because there are some advantages to use infrared astronomy, infrared light to study dust, because dust is transparent in infrared, meaning we cannot use the optical light to study dust because it has obscured our view of whatever is behind the dust that we see in the universe. In the past, since we didn't have telescopes such as JWST, we had very limited sample, and we don't have enough information. We have not investigated these objects as well. And James Webb Space Telescope provides the wavelength coverage and the sensitivity to colder dust that we never had before, such as with Spitzer. And we also can help us study fainter objects, so we can go deeper in the past and study a lot of objects with higher redshift. So I want to show you a couple of pictures to sort of demonstrate why we need JWST to study dust. So this is an optical image of a part of a sky taken with a normal camera. And then when you zoom in, it still is a better picture zoomed in using optical camera. And then another better picture with Hubble, same area. So now I'm zooming in on this optical image. And then here you can see this is zoomed in on this dark area in the center of the picture. So now you see this dark cloud here is what obscures our understanding or the light. So it sort of prevents us from seeing what is behind this cloud of dust. And then using near infrared or mid infrared and IR astronomy helps us to see what's behind the dust. So this image here is taken in the near infrared from 1 to 2 micron. And what you see, this cloud of reddish here, is this dark cloud that we can actually see through in the near infrared. And then in the mid infrared, which is what JWST provides mostly, is this image, which shows us how much more is behind that cloud of dust that we weren't able to see before. Are there questions? I can't see the chat. Please let me know if there are questions. So
yeah, nothing yet.
Thank you. So I'm going to tell you a little bit about James Webb Space Telescope. So this is a 6.6 meter telescope. It can help us observe from 0.6 micron to 25. It has 4 instruments. MIRI, which is the mid-infrared instrument. It has an imager and a spectrograph. There's NearSpec, which is the spectrograph that mostly focuses on the near-infrared from 0.6 to 5 micron. We have NearCam, which is a near-infrared imager, and then NIRIs, which is mostly the guiding camera. So here I'm showing you a comparison of Hubble, JWST, and Spitzer. So before JWST, the strongest infrared instrument that we had was Spitzer. So on the bottom right, you can see the comparison between the mirror of Spitzer, the middle JWST, and Hubble. Hubble has also the capability to observe in the near infrared, but it doesn't go as far. It goes up to about 1.7 micron. So now that I've told you why we use JWST to study dust, so the next question is, so what do we want to know if we observe dust, and what is the thing that we're after? So there are several questions that we're trying to answer after we get observations with JWST. So one is that we want to understand where dust forms in the environment of, let's say, a supernova or a star. We also want to understand if the dust is newly formed in a supernova environment, or if it was already existing in the ejecta of a supernova. We also want to understand how dust is heated, because if dust is not heated, we can't see it. So if we can see dust in, let's say, supernovae, then it must have been heated by some sort of mechanism. We also want to calculate the amount of dust so we can have a better understanding of the total dust budget in the universe. And we also want to have a better understanding of how dust evolves over time. So here I'm showing you a diagram. Since I'm focusing on supernovae and dust, I'm showing you this diagram that shows how dust forms in supernovae. So we start from the left. I've marked supernova explosion. So this is where with ground-based telescope, we detect a transient, possibly a supernova. We'll classify them, and then near maximum light is when we take a optical spectrum. We classify them if they're a 1A, a core collapse, and then after about 70 to 100 days, depending on what subclass of supernova the target is, we can start to see dust precursors. So by dust precursors, I mean carbon monoxide and silicon oxide molecules. So the reason we care about these molecules is that supernovae, when they explode, they're pretty hot, and they can destroy pretty much everything that is in their environment. So one of the reasons that initially people didn't believe supernovae can produce dust is because if they can form dust, they can also destroy dust that was already there. So the reason we go after these molecules is because carbon monoxide and silicon oxide molecules are the ones that are pretty common in space, and they can cool down by their vibrations. They can cool down the environment of supernovae to temperatures at which dust can form. So if, let's say, the temperature is about 5,000 Kelvin, we have a lot of carbon monoxide in the environment, they can turn down the temperature to about 1,000 or 500. And that's when the dust grains can start to form bigger dust grains, and then we can start to produce significant amount of dust. So if we observe supernovae or other transients with JWST, and then we look at the spectra or images and find evidence for these molecules, that means the environment of these supernovae are now cold enough to start forming dust. So we can start to study those supernovae, the observations, and then over time we can have a better understanding of how dust forms from early on to decades later. So at about 70 to 100 days, we look at CO formation, and then from 100 to 200 days, we expect to see silicon oxide forming in the ejecta of these supernovae, and we can see the features showing up in the spectra. And then after about 200, 300 days, we can start to see dust grains forming, silicate or graphite or alumina, depending on the composition of the progenitor before explosion. We can have any type of dust in the ejecta of supernovae. So what I'm focusing on is that I do find supernovae early on, and then we start to observe them from about 70 days post-explosion with JWST. We take data over about a year or two, and then several years later to see how dust forms early on, and then measure the amount of dust that has formed decades after explosion to have a better understanding of cosmic dust in the universe. So we have a lot of JWST programs that is focused on these right now. So what I'm showing you here is that, so I've sort of divided this diagram into three phases. Phase one is very early data of these supernovae and these molecules. And then phase two is where we sort of follow those molecules. And then phase three is when we look at the actual dust grains and dust compositions, which I've called logistical phase. And then these blue numbers and programs that you see are the ones that we have in cycle 1, cycle 2, and some in cycle 3 to focus on this topic. And what we're gonna measure is these molecules and the dust temperature, dust velocity, so we can have a better understanding. So first I'm gonna focus on the first part of this diagram, the early data. So this past March, a very nearby type 1c supernova exploded, called 23 dBc. So this type 1c supernova is a supernova that had already lost the hydrogen and helium outer layers before explosion. And the most significant thing about this supernova is that it was the most nearby in decades. So we triggered observations with JWST on the supernova to look at these molecules, see if we can actually see CO and SiO in their data. And we did, which was significant because it has never been observed before in this type of supernovae. So what I'm showing you here on the left is the spectra of this supernova from JWST using NIRSpec and MIRI. So NIRSpec is the near-infrared instrument, and MIRI is the mid-infrared. So on the top is NIRSpec spectrum going from 1.7 to about 3.2 micron. And then where I've marked carbon monoxide is where we expect to see a rise in the spectrum that shows there is carbon monoxide in the ejecta of the supernova. This was about 50 days post discovery. And then the middle one shows the red air filter of NIRSpec. This is another carbon monoxide feature that we can look at to confirm if there is significant amount of carbon monoxide in the ejecta, and we did. And then we also can see silicon oxide looking at using the MIRI spectrum, looking at around 7.5, 7.8 micron. So now that we observed this, it shows that maybe because type 1c supernovae, the reason that we see it at 50 days is because maybe since there's no hydrogen and helium, the outer layers of the progenitor before explosion, we can see the formation of these molecules much earlier, which could help us answer the biggest question that we have, that how is dust formed in the early universe? Type 1c supernovae that have lost these outer layers and form these molecules, these early on at around 50 days could be the answer to that question. There's another program that I'm working on. So this is also focused on early observation of supernovae, again, to look for these dust molecules, CO and SiO, but this time we used a different type of supernova. This time, the supernova was a type 2P that had the hydrogen and helium outer layers intact. And we wanted to compare this to the previous one and see what difference we find. So looking at this picture of this supernova, we actually didn't find these CO and SiO molecules, which means maybe because this supernova, the progenitor had the hydrogen and helium still intact, we can see these molecules, or it's going to form molecules much later, which means that probably by comparing these two, it's better we go after strip envelope supernovae to understand the early dust in the universe better. So we measured some properties of carbon monoxide in the spectra of this supernova to get an upper limit. So in the future, when we observe this supernova again, we can compare our numbers to what we have here to figure out how much CO has been formed in the supernova. And then observing the supernova gave us the first full spectral energy distribution of a supernova, going from 0.4 micron all the way to 25, which was never done before. And the photometry from JWST and all these spectra match pretty well. These are all different instruments. So the blue on the left is a ground-based optical telescope. The lighter blue is with a Keck NIRIS instrument at Hawaii Mauna Kea. And then the other two, orange and red spectra, are from JWST, and those gray dots are imaging with JWST. And all these match in flux pretty well, which was significant. We didn't have to do data manipulation to create this great spectral energy distribution. So that was those programs that we tried to study early dust and these molecules. Now I'm going to focus on what happens decades later. Let's say we have a supernova exploded 20 years ago, and now we're looking at the supernova to look at dust composition, dust properties, and what we're going to find. So there's another program that I've been working on. This one was a cycle 1 program. We had 5 supernovae that we selected. The reason we selected these 5 supernovae is because they were nearby. And if they're nearby, they're easier to observe over time, and they're not going to fade as fast, or they're going to be easier to get more data even with ground-based telescopes. So we selected these 5 supernovae because either we had evidence with Spitzer before that they had some type of indication that they had dust forming, or with ground-based telescopes, we had observed the first carbon monoxide molecule feature. So we got data for 2 of the supernovae in the sample last year. One of them is called 2004 ET because the supernova exploded in year 2004. And the other one is 2017 EAW, which exploded in 2017. So now we expected these 2 supernovae to have formed a lot of dust in their environment. And this time we wanted to look at actual dust grains, silicate, graphite, alumina, and whatever else that is there that's formed over the past decades. So first, I'm going to show you these images. So on the left, you can see this image with Spitzer that was obtained in 2005 of this supernova. And then on the right, you can see the image with JWST. You can see how much more we can actually see. This is the same exact field of view. We can see much more than we were able to do before. And the supernova, after about 20 years, is still pretty bright. And the reason it's bright is because it hosts significant amount of dust. And that reddish area around the supernova is a lot of dust that makes it bright enough for us to see it 20 years after explosion. Here you can see the other supernova, 2017 EAW. This image was obtained with Spitzer in 2018. And then on the right, you can see the JWST image of the supernova. As you can see, if you compare it with the previous image, 2017 EAW is not as bright. And just by looking at the image, we can say that it probably doesn't have as much dust. And since it's younger, it's not as bright as 2004 ET. So we had a press release on this program. So here you can see an image of both of them next to each other. I encourage you to take a look at the press release. It's called JWST Discovery of Dust in Type 2P Supernovae. So now this is a little bit of a detail on the work we did to study the dust and these two supernovae. So what you see here, these diagrams here. So looking at the one in the middle, 2004 ET. So those black dots are the 8 images that we took with JWST. So here, going back to this image, these images, how we did make them is that we took image of this supernova in 8 filters going from 5 micron to 25. We stacked them and we assigned a different color to each filter to create these images. So now another way to study supernovae is to plot them going from 5 micron to 25. And on the left, you can see the flux and the intensity of light in both supernovae. So what we did is that we tried to model the data of both supernovae using our dust models. So for 04 ET and 17 NAW, we tried graphite, alumina, silicate. So for 04 ET, since we don't see much of emissions, we concluded that it's probably mostly graphite or carbon, amorphous carbon. But for 17 NAW, since we see 2 distinct emissions, as you can see on the top right, those 2 distinct emissions are signature of silicate dust in the mid-infrared. And since we could fit them pretty well with our dust models of silicate, then we could get a temperature, and we concluded that most of the dust that we see in this environment of 17 NAW is silicate. So another question is somebody could ask, so why do you need one-on-one supernova? The reason is we don't have much data to understand how dust evolves over time. So here I'm showing you this diagram as the dust mass distribution versus phase. So all these gray points that you see from 100 days to 10,000 days are the dust mass measurements that have been done in the past using Spitzer. But you can see there's a huge gap when you look at the 2,500 days post-discovery to 10,000 days. We don't have any data points. And not having that doesn't allow us to actually model the trend of dust formation. So what we're trying to do is that we're trying to fill that gap, finding supernovae that are as old as 2,500 days to about 10,000 days, and see where they are going to be positioned in this diagram. So if I add those 2 supernovae that I just showed you in this diagram, so the green star is 2017 AW, and then the orange star is 2004 ET. So we have several more supernovae that we're still working on, and they're going to fill out this gap over time. And as we do that, then we can have a better trend of dust formation and dust mass over time in supernovae and ultimately in the early universe. So another fun fact about this supernova 2004 ET is that it has the highest dust mass observed in the mid-infrared with JWST. So before 2004 ET, the only supernova that was ever observed in the mid-infrared that had good information and good observations was 1987A, and it was pretty close. So there was a lot of sort of facilities that could observe it. But since then, we didn't have a supernova that nearby, and we probably won't have it for God knows how many years. So we won't have a chance to get a lot of good data of these supernovae, such as 87A. So 04 ET is the one that is the second supernova with the highest dust mass, with biggest observations in the mid-infrared after 87A, which was pretty significant. And we expected to see a lot of dust, but we didn't expect it to be this good. So if I want you to take away one main point from my talk, is that supernovae and observing supernovae is the key to probe cosmic dust. And understanding cosmic dust is important so we can understand the building block of the universe. JWST is the only facility that enables the study, and we also need more data. So we're trying to apply for more time in the future so we can fill out the gap and follow these supernovae over time and create a legacy data set. And I leave you with my summary. Thank you so much for listening.
Thank you so much, Dr. Shahbandeh. I've always been curious about cosmic dust. You know, as an amateur astronomer, it's just this dark stuff that we see in the middle of galaxies in our images, and I never knew what it was or where it came from. So that was very enlightening. I was always curious, like how it got formed, because when you think of dust as a layperson, you think of like really chemically complex stuff that's like gathering on top of the shelf here, right? But it's mostly carbonates and silicates from what you say. So
Right.
it makes a lot more sense as to how that got formed now. Very cool. We do have several questions that have come in, so thank you, folks. Got a few of my own too. I'm going to abuse my privilege here and ask one of my own first. So, you kind of like touched on the process of getting time on the James Webb Space Telescope. I see that a lot of these observations are time sensitive, where you're trying to like measure the spectra at distinct windows there. How do you do that? Like, there's got to be a ton of competition for that time on this thing. So what's the process for actually getting these observations that you need and getting more data?
It's actually very hard to do. So for this supernova that I showed you earlier, 23 dBc, so we got actually the Richter discretionary time, which is even harder than normal cycle. So first I want to say that JWST time is public, so anybody can propose. Usually it's about 8 pages that you need to write about your science and technical. So it's about half science, why the science is important and why JWST helps, and then 4 pages on technical stuff, like what instrument you need, how much exposure time you need. And then there are some software like APT, it's called APT, that you put in all those numbers and the science that you want. Let's say a spectrum of a supernova that is 20 mag in optical. And then you get some exposure time, like 5 hours on mid-infrared instrument, JWST. And then you write the proposal. But yeah, the competition is pretty high. So I think in cycle 2, there was about 5,000 or 6,000 proposals submitted. And it was 5,000 hours. So the oversubscription, sorry, I forgot the word. It was 10 to 1. So out of every 10 proposal, 1 gets accepted. So I guess the reason we got these proposals is because we really spent a lot of time, like months and months, on calculating all these details of like what instrument we need, how much time we need, and there's a lot of overhead on JWST. So if you have you need 2 hours of exposure on a supernova, you need 2 hours overhead, just slewing and changing instrument and all that kind of stuff. We got a lot of DDT time, which is only reserved for, so it's a director's discretionary time that reserved for transients, such as supernovae that explode out of a sudden. It's like a main event. You won't have a chance to observe it later on if you wait till the annual cycle deadline, which is in 2 weeks. You won't get the chance. So for this type 1c supernova, we about a week or 2 after it exploded, we actually submitted a proposal, and we sort of emphasize why it's important to get this one, because we really don't have these strip envelope supernovae that are bright enough, close enough that we can observe them. If we didn't get this time, we probably wouldn't not be able to do a JWST for the next 20 years.
Wow.
Did I answer your question?
Absolutely. Thank you. It's very cool. Can't imagine that world. We got a ton of questions, so I want to try to get through them. Kind of tied into that a little bit. Bill Castro asks, where do you get your information or alert that a supernova has happened that you'd want to observe? How do you find out about them?
So there are a lot of ground-based telescopes that take an image of the sky every night, such as a ZTF telescope or other optical telescopes, or a lot of amateur astronomers. So if I'm after a supernova, or like if I'm after, let's say, finding a good event, then I would stay up overnight sometimes, looking at all of these alerts that come from these telescopes and go through maybe 300, 400 different alerts, which is these ground-based telescopes. They take an image of the sky tonight, and they take an image tomorrow night, and then they compare them. So if there is a new like bright point somewhere, that means it's probably a supernova or other transient. So those are the alerts that are public. They're on transient server name, and what I used to do is go through them, look at all these bright points, like 300 or something every night, and see if they're real. A lot of times it's easy to see if they are real. You can see a lot of satellites and that leave a trace, so they are picked up, but they're not actually supernovae, or there are bad pixels, this kind of stuff. But if they're good, then amongst maybe like 400 different alerts every night, we'll find 10 good ones. And then out of those 10, we wait for a classification spectrum, maybe the next night, 2 nights from now. And then we can see if it's an important target to follow.
Very cool. Hear that, folks? Amateurs can actually contribute to that. So
They do actually, yeah.
Very cool. John Pinto, going back to toward the beginning of your presentation, asks, what is an AGB star? That's a new one for us.
So they're asymptotic giant branch stars. These are stars that shed their outer layers over time, but they're not massive enough to explode like supernovae to spread material throughout the universe. But since they shed their outer layers, that's why initially it was thought that these stars are the ones that actually produce those significant dust that we observe. But then when they measured the dust and they realized it's actually way more than what AGB stars could produce, then everybody sort of came up with the idea, oh, it could be supernovae that explode. They're pretty massive, they explode and efficiently spread material throughout the universe.
So we're talking about the kind of star that produces like a planetary nebula where it's blowing off that outer shell.
Yeah.
And that's what our own sun's supposed to do someday, right?
Yeah, sort of.
Sort of.
Maybe not. It's not as massive, but yeah.
Okay, so we're kind of a level below that. But maybe we'll produce some dust. All right, got a few from Luke Corwin. What is alumina? I have to admit that's a new term for me.
Yeah, so it's any dust that is made of aluminum.
Okay, stuff made of aluminum. That's easy.
Yeah, so like when we say like silicates, so the reason so when we say silicates, it's not necessarily exactly just silicon. It's like silicate oxide or silicate plus magnesium, but it's mostly silicate grains. So or graphite or alumina. It's the main composition for that dust that we observe is, let's say, aluminum. That's why it's called alumina or silicate or graphite.
Right. Cool. Thank you. Also from Luke, and Luke, feel free to come off mute if I'm mangling your question. I didn't quite understand what you said about strip shell supernovae. Are dust precursors absent in these? And if so, why are they valuable for studying dust?
So actually, we didn't know if dust precursors are absent or they're present in these supernovae because they were never observed before. So we actually, this 23 dBc that I mentioned is the first one ever observed of a strip envelope. So a strip envelope, the reason we call them stripped envelope is because, so let me go back to this image. So on the, if I can move this, so you can see that here. So on the top right, you can see, so normally for a massive star, we usually have this hydrogen layer intact, and then we have helium, and then we have all these other layers. So some of these, due to having a binary companion, like another star there, or because of some winds or some other factor, they lose some of these outer layers, such as hydrogen and helium. So if they've lost those outer layers, we call them stripped envelope, because they've lost this envelope around them. So if they've lost this envelope, it's easier to see through the core of this star, because hydrogen and helium don't allow us to see through. But if they've lost that, then we can easily see carbon and core of the supernova, and the envelope is no longer there. So we expected, sort of, for strip envelope supernovae to see these molecules earlier, because they don't have this hydrogen and helium. So if these molecules form around the supernova and we don't have anything to block it, then we can see it much earlier after supernova explosion, compared to a, let's say, type 2p supernova, which still has their hydrogen and helium intact before explosion. Does that make sense? Did I answer your question?
I think so. Luke's not complaining, so I think that was good.
Well, and the other part of the question I had was, then what did you actually see when you looked for that in this supernova you observed?
So we actually saw the molecules, because people didn't believe strip envelope supernovae. Actually, maybe that's one reason we got this proposal accepted, because nobody believed that strip envelope supernovae can be behind the main dust producers in the early universe. But since strip envelope supernovae come from the most massive stars explosion, we proposed that we can see it in the spectrum. Let's take a spectrum of a type 1c and see if we can find these molecules, and we actually did. So we saw the carbon monoxide, we saw the silicon oxide at 50 days, which is significant, because normally people go after type 2 supernovae, the ones that still have their hydrogen intact, and they see it after about 150, 200 days. But we saw these molecules forming at about 50 days, which means at about 50 days, the environment is already cool enough for dust to start forming. So we have other observations of this supernova coming up in December and some next year, that we can get more data and see how much these molecules have evolved, and if we can start to see, let's say, silicate or graphite. Does that answer your question, Luke?
Yes, thank you.
Cool. All right, last call for questions, folks. Do hit that Q&A button if you want to sneak one in at the end here, but got one more here, also from Luke, asking about the possibility of a nearby supernova in the future. He's heard that we're overdue for a galactic supernova nearby. Is this not true?
So I don't know. I don't think so. Well, we're going to have JWST for at least 19 more years, which is great. But I don't know, maybe, but I don't think we're going to have anything as nearby as, like, let's say 1987A. This supernova that I'm showing you here, this was the closest in decades that exploded. And it has a lot of actually good observations from the ground too, because not even if we didn't have JWST, we still would want to observe this with ground-based telescopes. And another supernova that actually exploded recently that was pretty nearby is called 23IXF, which is a type 2p that we also have a DD time on. And we tried to observe that, and we didn't see the molecules in that supernova. But the chances are not high. So we're trying to propose time in 2 weeks for cycle 3 to get more observation of this specific type 1c and the other nearby type 2s that we found. So we can sort of create a legacy data set with JWST from explosion all the way to hopefully 20 years from now. So eventually we can have a ultimately better understanding of cosmic dust.
All right, so don't believe the hype about Betelgeuse then?
Not really.
All right, good to hear a professional opinion on that one. There's a lot of hype about that. All right, one more from Frank Fortanese. Hi, Frank. You have a good name. How often do supernovae take place that we can see?
Generally,
Yeah.
I think right now that we have a lot of good sort of sky searching telescopes from the ground, there are about maybe more than 1,000, about maybe 1,000 to 2,000 a year. I may be wrong, but it's around that per year. But not all of them are good enough to be observed with all different telescopes. And with JWST, the reason we went after these very nearby is because we wanted to observe them for decades. So if they get pretty faint, like let's say in a year, then it could be really hard, and we don't want to waste JWST time. So that's why we went after these nearby ones. But from the ground, we have a lot of other near-infrared telescopes that we can observe these supernovae up to maybe 2 months, 3 months, depending on how bright they are. But usually we get about 1,000 a year. And if we talk about good ones that we can actually do a lot of study on, I don't know, maybe like a couple a month.
Wow. They're just popping all the time. A good testament to just how many stars are out there. Kind of tied in, let's do one last question from Bill Castro. How faint in magnitude can JWST see, and how bright is too bright for its instruments?
So how bright is too bright? So we do use the exposure calculator to not explode the detector. So I guess it depends what instrument we use. If we use mid-infrared spectrograph, then we can go brighter with shorter amount of time. But maybe like I would say 16, 17 is just too bright. How faint? I guess maybe 26, 27. Does that answer your question? But it also depends on what instrument. So like if you want to observe it, supernova that's 26 magnitude, or any star, 26 mag, then you have to expose for hours with these instruments. Sometimes it's just not worth it. Like there are actually transits that are interesting that we would want to observe, but if you have to focus telescope for 2 days on one target, it's just not worth it. So we don't do that. And it's very hard to get time to do that. But yeah, probably 26, I would say.
Excellent. I think we all have a case of telescope envy now, but that's understandable, I think. Well, thank you so much for your time tonight, Dr. Shahbandeh. This has been a good reminder that JWST is about a whole lot more than making pretty pictures. So there's some pretty cool science going on here too. Really appreciate your donating your time tonight. And
thank you so much.
Yeah, it was
thank you for having me. Yeah, it was a pleasure to be here. Thank you so much.
All right. Thank you. And you're welcome to hang out if you want, or get back to your life. It's up to you. So let's.
I'll be hanging out here.
Cool.
For a while. Thank you so much.
Thank you. All right. Let me hand it off to John Pinto. Let me give you sharing privileges. And we're going to say the dirty A word, aren't we?
Yes, we are. Yes, we are. So let me share my screen. And here we go. And I want to share my PowerPoint, and we're going to share that. Let's go to presentation mode. There we go. Okay.
Yep, there you go.
Excellent. Okay, astrology for astronomy. We're going to use the Old Farmer's Almanac, which is a nice and expensive astronomical, actually, almanac. It was actually how it was started in the 1700s, because back then people really were interested in astronomy and the sky. They didn't have, all of our entertainment that we have today. So they were interested in this kind of stuff. So let's see what kind of information we can get out of it. So before we talk about, let me just rise myself over here. So before we start talking about what you can get out of the Farmer's Almanac, Old Farmer's Almanac, we need to talk a little bit about what I'm calling a universal astronomical calendar. So I'm going to put this image up in Groups.io so you guys can print it out and use it as I'm going to explain how it can be used. And I'm going to do future mini programs on this astronomical calendar and other ways you can use it. Today, we're going to basically be focusing on the moon, but it has many, many other uses. The first thing you'll notice is that it has the ecliptic drawn in, okay? And the ecliptic is basically the path of the sun through the sky throughout the year. It also has what's called the celestial equator, which goes right across the center here. And those two things are really important to understand if you're going to go outside and observe visually and you don't have a go-to telescope and you're just trying to understand the sky. So let's start with the equator. Okay, so the celestial equator is basically a projection of the Earth's equator out into space. And the way you can visualize that is if you were to face due south, get a compass out, take out your cell phone and turn on the compass and find out where south is if you don't know where that is. Face south, point your left arm straight out, point your right arm straight out, and they'll be pointing to east and west. Okay, so south is in front of you, east is to your left of you, and west is to your right of you. And I'm doing it from Florida, right? If we were in South America, it'd be totally different, but we're always talking Florida here. The next thing you want to do is you want to, again, from Florida, we are about, say, 30, I'm rounding things off. We're like where we are today, we're around 30 degrees in latitude above the equator. So what that means is that from the top of your head, right, if you pointed straight up and you went down 30 degrees, that's where the top of the equator is in the sky. So if you were to, take your arms that you just spread out and just arc them up to about 30 degrees from the top of the sky, that is where the celestial equator is in your sky. And everything is related to that. Now, the ecliptic doesn't go as nice and smooth like that is. It goes above the equator for certain parts of the year, and it goes below the equator at other parts of the year. And what does that mean? So that's what causes our seasons. So when the sun, say over here in June, right? The way this astronomical calendar works is you find the date that you're interested in, so middle of June, you cross over to the thing you're interested in, so let's say the sun, and then you go up to where the ecliptic is, and that tells you where the sun is going to be at that time of year. So in June, the sun is in Taurus, and you can see it's very high above the equator. Well, that's what causes what we call summer. Now let's go to, say, I don't know. Let's go to December, okay? So in December, where is the sun? So we know that winter solstice is around about the end of December. So if we go down here and we say, well, where is the sun in December? And we look down here and say, oh, the sun is in December. So it's around here. The sun is way below the equator. Oh, guess what? That's what we call winter. So when the sun is over here in this part of the ecliptic, we have summer. Down here, we have winter. Okay, so that's really basic understanding of how this astronomical calendar works. All right, so the next thing to understand is here in our modern day, 20th century, most astronomical events are usually related to the equator. Their coordinates, right? Or they, right? What we call right ascension, right? So don't worry about the name. It's just a way we measure things in the sky. And usually today we do it based on the equator. However, in ancient times, because they weren't so much interested in that, they were more interested in where the planets and the moon were, they were more interested in finding out where things were along the ecliptic. So what they did back then is they actually named portions of the ecliptic based on constellations. So you have Aries and Taurus and Gemini, etc. So every 30 degrees in the ecliptic has a name, and today they're called the zodiacal signs. That's where the astrology piece comes in. But ignore all the things about, what does it mean to be a Taurus or a Gemini? That's not what we're focusing on. What we're focusing on is the regions of the ecliptic. So the Aries region of the ecliptic is the first 30 degrees in the ecliptic. Taurus is the next 30 degrees. And one of the things you're going to notice is that the signs, right, those portions of the ecliptic with that name, don't match up with the constellation that's there, right? So the sign of Aries on the ecliptic is where the constellation of Pisces is. Where the sign of Taurus is where the constellation of Aries is. So, why is there such a mismatch? Well, the early astronomers / astrologers, because you got to remember, way back when, there was no distinction between the two. The constellation of Aries was actually where the sign of Aries is. So the signs were named after the constellations that were in that portion of the ecliptic 2,000, 3,000 years ago. Why did they move? Well, there's something called precession, which is sort of like a wobbling top, which is what the Earth is. And over, the centuries, these constellations move to different portions of the ecliptic. It takes about 26,000 years for it to make the full circuit, but that's why the constellations are a little off from where the signs are. So we're going to focus just on the signs for the moment. So now that you kind of know how this works, we're now going to go look at what the Farmer's Almanac can help us with. All right, so in the back of the Farmer's Almanac, which I told you is really an astronomical almanac, which has a lot of good astronomy in it, and I'll do future mini programs on more of the information that's in here. But the two pieces I want you to focus on here is on the left, okay? And what this is telling you is what, if you don't know what those symbols meant, right? I don't remember what that symbol means over there. The Farmer's Almanac will tell you. So that is Scorpio. Oh, that's Gemini. Oh, that's Taurus. Okay. And it also tells you where the sun is in that, and when the sun will be in that sign during this portion of the year. Now, these are averages, right? So sun moves a little bit different every year. So maybe it's not June 20th one year, maybe it's June 20th, maybe it's June 22nd. And a lot of that has to do with leap years. But in general, that basically tells you where the sun is. Okay, so right now we're in October, so the sun is in Libra. Okay, so that means over here, well, let's get the sign here. So Libra looks sort of like that thing there. So if we go over here, that's this guy here. So here is where the sun is, and we're in October. Oh yeah, that makes sense. Here's October, and the sun is in Libra. Okay, I'll tell you why that's important in a second. So the next thing I want to know is this other table that's in there, which they call the moon's astrological place. Ooh, the bad word. All it's really telling you is where in the on the ecliptic is the moon. Okay, and each day of the year, it tells you where the moon is. Now, you can't use this chart from year to year because the moon is moving so quickly around the Earth that what particular sign it will be in on any particular day changes every year. So you really do have to buy a new almanac every year. Very inexpensive, and I'll show you that in a second. So again, let's take October, and we are October 11th, right? So October 11th, we see that the moon is in Virgo. And I'm going to look a little bit further, and there's a funny thing that's happening on October 14th. And at that point, the moon is going to be in Libra. The sun's in Libra. The moon's in Libra. What do we think happens when the two things line up? So when the sun is in Libra in the middle of October, and the moon is going to be here too, oh, that's where you have eclipses. That's when eclipses occur. Eclipses occur when the sun and the moon are in the same sign, plus one other extra special thing that the almanac will tell you if you know where to look, but I'm not getting into that today. But there's something, and Derek talked about this at the last program in the planetarium. There's something called a node. And when the sun and the moon and the node all line up at the same point in the astronomical calendar, that's when you can have an eclipse. So what's a node? I'll do that real quick. So as I said, the ecliptic is where the sun is. So we already know where the sun is, right? It's going to be somewhere on this graph here. But the moon does not follow exactly this path. Moon is kind of a wandering mistress, let's call her. So sometimes the moon is above the ecliptic. Sometimes the moon is below the ecliptic. Sometimes the moon. So this is basically how the moon moves around the ecliptic. Goes down and up and down and up. Well, whenever the moon crosses the ecliptic, that's called the moon's node. And that actually tells you why this is actually called the ecliptic, because the moon has to be at the node in order for an eclipse to occur. And that's where the word ecliptic came from, because eclipses always occur when the moon is on the ecliptic. So eclipses, ecliptic, they're related to each other. It just turns out that this year, the node of the moon is right about here. Okay, one of the nodes. There's actually two nodes. There's a node when it goes down, and there's a node when it goes up. So if it goes up, that's what they call an ascending node, and when you go down, it's called a descending node. So actually, the descending node is around here right now, which is telling us, yep, we got very good possibility we're going to get an eclipse here. The other node is around here somewhere, and next year we'll probably have some eclipses that are occurring at the ascending node. So there you have it, a little bit of astrology in teaching us something about astronomy. And this was just a little slide to kind of highlight those sections that I was just talking about. If you are interested in getting your O-Formers Almanac for 2024, they're out there now. If you want the actual print version, you can get it for about $10. I picked mine up at Barnes & Noble the other day. You can just buy it online as an ebook for $7. And they also have a feature at almanac.com, which is the website for the Almanac. You can actually put in Orlando, Florida, and they will print you out a local Almanac page, which basically tells you, when the sun's going to rise, when's the moon going to rise, and other kind of interesting information specifically for Orlando. So that's, I do that every year. It's just a good, handy tool to have. And that's it. And like I said, future months, I will show you a few more things you can do with that astronomical calendar. Don't know if we got any other questions, but that's my talk.
Cool. Thank you so much, John. You just gave me an excuse to go to the bookstore, which is always a good thing. Very cool. All right, let me, now you get to watch me fiddle around with screen sharing. Let's see if I can figure out how to get the Astrophotography Showcase going here. No, not that screen. The other screen. You would think we can operate telescopes, but we can't operate Zoom. All right. Hang on, folks. Move that out of the way. Share screen. What? That screen. All right. I think we're in business. All right. So yeah, let's do our Astrophotography Showcase. And hey, John, just real quick, are you seeing the correct view there? There's no weird windows.
I just see you.
You just see me. How about now?
Now I see an Astrophotography Showcase.
Yay, I did it. All right. So as always, we're going to go through our submissions for this month. And there is, as always, a surprising amount of them, given that the weather has been absolutely terrible the past month. Somehow, you guys produced some sketches and photos. And some of you cheated by traveling, but that's okay. We'll share that anyway. And if your photo comes up or your sketch comes up, I will hand over the virtual mic if you're here to talk about them in your own words. So up first, we have Bill Castro. I think you're still here. Let me find you in the list and hand over the mic. Oh, William, you earned a W. Confusing me. There you go.
Okay, hopefully you can hear me.
Yes. Let's there you go. What? All right.
There we go. I can see it now. And I've been working on the Astronomical League's Sunspotter Observing Program. So here are two observing logs and sketches of sunspots for the program. And these are sketched 2 days apart. You can see the spots change and move across the disk. And with this program, I've learned how to come up with a Wolf sunspot count. That's recorded on the log sheet in the middle left. And that's 10 times the number of groups. And then from that number, you add the total spots to get that number. And the other thing is I've learned the 3-letter Macintosh sunspot classification system, and that's recorded in the lower left of those logs. And that system is used to predict upcoming solar flares. And in the lower right is a picture of my solar observing equipment. And you don't need a large scope. You use whatever you have is what they tell you. And you do need a white light filter, not a hydrogen alpha or anything else. And to be consistent with the decades and years and years and years of sunspot counts, they prefer you use a smaller scope, 80 millimeter, 90 millimeter, something like that, and do it visually. I thought that was interesting.
Very cool. And this is also a good plug for the Astronomical League Sunspotter Observing Program and everything else the AL does. We just happen to have our Astronomical League coordinator for the club with us as well, which is one of John's many roles. John, you want to say a few words about the AL and how that relates to CFAS?
Oh, definitely. Actually, I had a question for Bill about the program. Bill, did they talk in the program a little bit about the? I know that there's something about the magnetic direction of the sunspots, whether they're north facing or south facing, and how that changes and how that affects flares and things like that.
Yeah, they did. There's a Observe the Sun manual, a PDF that you can download, and you want to read that to fill in all the information. It goes into a lot of detail, and it talks about the magnetic poles. It's a unipolar, bipolar spot, whether they go that leading forward or backwards. Tons of information on sunspots that are there. I was pretty impressed with that.
Yeah, and that's sort of why I wanted to kind of push our members who are interested in really diving deeper into various aspects of observing to get involved with the Astronomical League's observing programs, because you will learn a ton of stuff that, it's way below the surface of, what we can do in mini programs. And you will learn, you'll become, you can almost get a PhD in some of these things from the level that you can take it to. There's simple observing programs. There's, more in-depth observing programs like this one that Bill's been doing. So you could, pick your level of interest. They even have observing programs for kids. And in the end, if you, follow the directions and you fill out the logs that you need, you get a certificate. Bill, you've done a few of these. What are the certificates like? Is it just a piece of paper, or is it, a little fancier?
You get a piece of paper. They give you a pen, and some people don't really submit the information for the award or pen. You can just do part of it, or you're not getting paid for it, so it won't show up on your annual review or anything, whether you complete it or you get an incomplete. You do whatever you want. The whole thing is you can learn a lot of things. I've been, an amateur astronomer for pushing 30 years now, and I've been doing these programs. I'm still learning things. A good example is the Urban Observing Award. I went through that list. If nothing else, it's a great list that you can see objects in your light polluted backyard, suburban Orlando area. and all of those things are within reach of, an 8-inch scope. And there was like 3 or 4 new objects that I'd never seen before on that list. I was surprised.
Oh, terrific. Yep. So everyone who's a member of the club is automatically a member of the Astronomical League, and you are welcome to go to the Astronomical League. Just Google Astronomical League, and you go to the observing program section and see if you could find a program that you'd be interested in, and just get started. And I'm the coordinator, so if you have questions about it, or you have completed it and you want to submit your logs, you can send them to me via our website, which you can groups.io. You'll see how you can reach me, and I will submit it, and hopefully you get your certificate and you can put it on your resume.
Very cool. Thank you so much. And that was a shameless Astronomical League plug. Up next, Sharifa Gassel, who is not here because she is someplace far more interesting. And I see your dad, Yamil, is here. Not to put you on the spot, but you can probably talk about what's going on better than I can. Do you want to say a few words about these next couple of images, Yamil? Guess we don't have the microphone going there, but the short story is Sharifa is out in Hawaii at the High Seas facility. This is the analog Mars and Moon environment that's run out there that NASA uses for simulating long duration missions. And as we speak, she is beginning a 2-week stint out there studying the effects of long-term spaceflight on psychology. So how cool is that? I expect a very good trip report from her when she's back, because wow, the story she's going to have. And this is a shot that she took from the site there before they locked her up. This is on the slopes of Mauna Loa at about over 8,000 feet up. So you can imagine the skies are pretty darn good there. And this was just a 10-second exposure she took from that site, which is pretty awesome. And I think she shared another one here as well, which is even better. I have deep envy going on right now. And the specs on that image are, like I said, just a 10-second exposure, ISO 3200. You're just using a Sony ILCE 6000 camera. So how cool is that? Again, when she's back, I will be begging, borrowing, and doing whatever I can to get a mini program out of her about what that experience was like. Because, wow. I hear she also got a tour of the Keck Observatory while she was up there. So, yeah. Must be nice. Meanwhile, on Earth, I've been doing a little bit of imaging myself. This is the Cave Nebula, imaged over, I think, 3 nights. This is kind of a challenging object to get. Obviously it's a nebula, and there's a lot of there's some star formation going on there. You can see that kind of like backlit cloud of dust, which we just talked about earlier. That's kind of obscuring some newly formed starlight there. But capturing that sort of blue ionized oxygen glow around it is pretty tough from light polluted skies. So it took quite a bit of exposure time to bring in that blue there and try to make this a little bit more of a pretty picture, because otherwise, it's a faint one. It's a tough one to get, but I'm still happy with it. Specs on this was an ASI ZWO 2600 Pro camera in a Mach Newtonian telescope, a Skywatcher MN190. And Wes,
hey Frank, that's a lot of cosmic dust.
Indeed, look at it all. And now we know where it came from. Wes, let me give you the mic.
Yes, sir. Can you hear me?
Yes.
Yeah, here we have the elephant's trunk, which you did last time, I think. I think this is a little bit of a tighter view. This was imaged from my backyard here in Winter Park, and most of it actually was done under a full moon.
Wow.
And it's about 20 hours, just short of 20 hours of exposure time. And I just love it's my first long exposure nebula shot with my Edge HD. So I'm pretty happy with how things are turning out with it. I'm pretty excited. So this was a Celestron Edge HD 8-inch with a ASI 294 monochrome on it on an EQ6R Pro.
Nice. And how many hours were on this one?
Just short of 20. Most
It
of it was
shows.
on the O3 and the sulfur.
Exactly. Yeah, that O3 and sulfur is tough to capture under light pollution for sure. But great results there. And yeah, a little bit tighter review than what I got as well. So well done. That reminds me, by the way, we're thinking of putting a astrophotography gallery on our website sometime soon. So I'll be soliciting contributions for that shortly if you're interested.
Wonderful. Yeah.
Yeah, kind of let people see what we're doing a little bit more widely. Up next, we got Eric Moore. Let me see if you're here. You are. A couple of images from you. Want to talk us through this?
All righty. Can you hear me?
Yes.
So the photo on the right, when I joined the group, I got excited and booked a couple of trips down to Kissimmee Prairie. The first of which, rookie mistake, didn't realize it was a full moon, but I went anyway. The weather was terrible. Didn't get any shots of the Milky Way. The second trip I booked was on a new moon night. The weather again was terrible, raining, but I managed to get the shot that I was excited to get, being there by myself with all the mosquitoes. But the only thing that I was challenged with was getting those stars in shape really crisply. I couldn't align the Polaris and use my tracker because of the clouds, but was happy to get it. That was my goal. The one on the left actually went out to Montana in July, I believe, and I was able to capture the Milky Way up in Big Sky at the Lone Peak Resort. You can kind of see the ski lift chairs there at the bottom. Didn't really know. I kept getting those greenish blue lights to the left, and I thought it was an alien or something trying to contact me or something. But someone eventually said that's lens flare.
Right.
But had a good time out there looking around me for bears that may be coming my way. But Big Sky, still a lot of clouds, was still unable to track this. So these are single shots, I believe, probably 40 seconds or so. ISO 2000. So had a good time.
Very cool. Very cool. Yeah, bears. Remind me the next time you see me in person to tell you my story about chasing off the bears at the top of Glacier Point in Yosemite while trying to do some observing up there. Good times. Oh, man. John Starr, got a couple from you as well. Let me pass over the mic.
Oh, hey, can you hear me?
Why, yes.
Oh, gotcha. Okay. So this is these are a couple months old now. This is a shot of the meteor shower. And so I took this at Ocala National Park. I was literally eaten alive by mosquitoes out there. And it was pretty much cloudy all night, but for an hour or so, and I was able to get this shot. So I can't remember how many. I think this is 20 or 23 sort of shots stacked on top of each other. It was so dark out there. I left my lamp on top of my car, and so used that bright spot kind of on the ground there as the lamp sitting on top of my car. But this was a fun shot to get. I was the only one out there. Not a lot of people camp in the middle of summer in Florida. So, but it was a really nice night, and it was quite the show. So I'm kind of pleased with how this came out.
Yeah, it's a beautiful image. Great composition. Love it. And the sun.
Yeah. So this is a shot with two different setups. So the shot on the right is with the Lunt 40 millimeter, and so this one was just on a star tracker and using sort of a little planetary camera, and I don't know, it was maybe a 10-second or 15-second, some lucky imaging, and stacked 50 or 75 or so. But I was really, really pleased with how this LUNT is performing. It's such a small scope. It feels like a toy in your hand. It's so small, but it really, really puts out some pretty amazing views. The shot immediately to the left of that is a shot that I took right after, and this I used essentially the quark chromosphere model, Daystar quark chromosphere model with a Skywatcher EvoStar 72. And so that quark has like a 4 times Barlow built in. So even though it was a very similar focal length, the effective focal length was much greater. And so I was just trying to see kind of what the difference was the two in terms of how they performed and that kind of thing. So that shot on the left is a zoomed shot of the sort of the upper left quadrant, sort of the sun there.
Yeah, and thanks so much for turning me onto the LUNT 40. I bought one of my own, and we'll be streaming the eclipse with that on Saturday. Yeah, I'm very impressed with it. So thanks for the recommendation. Also, have you tried putting a Barlow on the LUNT yet?
I did do that. I did put a Barlow, and it was all right. I have the slightly larger sort of diagonal. I think I have the 1200, and so it fit, and it sort of worked out well for me. But I probably won't do it again, only because I have this Daystar quark, and so it's that when it's pretty flexible, I can put it on different scopes and stuff like that. But the LUNT 40, I'm packing right now because I'm actually flying out to Albuquerque in the morning to hopefully shoot the annular eclipse on Saturday, and I'm going to bring that little LUNT 40 with me. See what I can get.
Oh, that's awesome! All right, I wish you clear skies. That's pretty cool, and I'm looking forward to your images from that next month for sure. Cool. Douglas Woods, are you here? You are. Oops. There we go.
Oh man, that didn't come out too well.
Looks good on my end.
Well, I
What are we
did the
looking
best
at?
I could to get you one that was in an expanded format.
Oh, okay. Yeah, that was the JPEG one that you sent me later on that was zipped up. So
Okay.
definitely better resolution than the original one. So let's just go with it.
Obviously, it's the Aurora Borealis. It was one of the main things I wanted to accomplish when I went to Alaska recently. It's not easy, as you might imagine, to get a picture of anything on a cruise ship with all the lights blowing along at about 22 knots on a mildly choppy sea. It was a challenge, but what I found eventually was that using my Canon R6 and a Tamron, that's Tamron, not that other thing that autocorrect keeps screwing me over with. F1.4, that's the 35 millimeter, 4/10 of a second, ISO 5000, and I was shooting at f1.4. I got a couple of hundred of these images, and you might notice something very familiar above the aurora. ... Oh, nobody else can say anything. I'm sorry. Now, obviously, it's the Big Dipper, and it was the highest, obviously, I had ever seen Polaris over the horizon.
Oh, there it is. All right. Yeah. Cool.
It took you a while, eh, Frank? All right.
It did. It did. It's been a long day. Yeah. But yeah, I see it now.
But like I said, it was a challenge to get the picture, and like everything else on my Alaska trip, it didn't quite live up to expectations. While it looks like this through a camera lens where you can adjust the settings, naked eye viewing it with no night vision to speak of, it looked like a white cloud, and not as this wonderful streaky, thank God the sun was active, aurora. that I was able to image.
Interesting.
There were a lot of times I was out there with a tripod, which put me one up on anybody else trying to take pictures off the ship. But there were people who were out there looking for the aurora and didn't know that they were looking at it until they saw it on my camera screen. It
And
didn't
this wasn't
really
even that
look
long of
like
an
much.
exposure, right?
Pardon me?
This isn't even that long of an exposure, right?
No, if you went any longer than that, everything would get kind of streaky. And
Right.
if I bump the ISO up much higher, it would get noisy. So, in any case, I was able to at least tick this off my list. I enjoyed it. And I'm not going back to Alaska unless I'm going to do it on my own 2 feet. No trains, no buses, no boats.
We share the same opinion about travel, I think. Very cool. But yeah, that's a bucket list thing for sure. I've never gone to see the aurora, but someday I hope, which is frustrating because I used to live in Seattle, which is like super high latitude, but it was always too darn cloudy. But so I'm glad you got to see it, Douglas. That is very cool. And with that, I think we are done. So yes, that wraps up our meeting for October. Thanks to everyone who hung out with us here tonight. We'll do it again next month, tentatively scheduled for November 8th, another Wednesday. Breaking news, I think we might have to move that to a different week, but stay tuned in Groups.io for any details on that. Again, looking forward to next month's presentation on neutrinos from Luke Corwin. So thank you, Luke, for having that ready to go. And as always, keep looking up. See you guys next month. Thank you.